Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to the class of CS352 Introduction to Soft Computing, Lecture 9, Section 9.4, where we'll be talking about control systems and AI, specifically an application of fuzzy logic in a room cooler. In the previous sections, Section 9.1, I had basically introduced you to the concept of fuzzy logic. In section 9.2, I had talked about fuzzy sets and the mathematical background and foundation for fuzzy logic. Then in section 9.3, I had talked about what fuzzy inference processing is, what are the key components, what are the designing factors for FLCs, fuzzy logic control systems, and we had basically seen a small glimpse of what is to come in this lecture, which is going to be the application of fuzzy logic for a case study that is going to be a room cooler and how we're going to work on it. So let's get started with this. This is the last lecture for the course of CS352, and maybe I'll have just one more lecture which will be on the overall course review, including, like, we've basically studied 9 topics here, and I'll kind of give an overview of all the 9 topics in the next lecture. But so this is the last lecture on anyway on fuzzy logic and control systems and AI. Okay, so the question here is, can logic be fuzzy or ambiguous? We're going to see through a case study on fuzzy controller in room cooler. So the agenda for this section, well, there's only one agenda here, and that agenda is that we are going to see the application of fuzzy logic on a specific system. In this case, it's a room cooler, and we'll see the different rules, and we'll apply the fuzzy logic rules on this room cooler system. Of course, there's another thing that we might discuss, and that is basically the key application areas on which fuzzy logic has been applied. And you'll see the pattern there as well when it comes. Okay, so here is the case study, and we've seen this problem statement earlier. A room cooler has a fan encased in a box with evaporative pad or wool or hay, for example in case of a Lahori room cooler. And I've already said that the physics rule that works here is the rule of evaporation, where when water evaporates, it basically cools, it absorbs the heat from the surface and cools down the air. So they're going to use this to take water up from the bottom. They basically need a motor that basically pulls or that pumps the water up, and after pumping the water up, it flows down through the evaporative pad or wool, which is continuously being moistened by the water, and hence the cooling occurs. The air gets cooler, and hence you get cool air in the air in the room. So there are two things here. The rate of flow of water, which is basically your output. We want to determine the rate of flow of water, and it is a function of room temperature and the speed of motor. So the more the water, and the speed of fan, actually, not of motor, and the more the speed of fan, of course, the cooler the temperature will become, and similarly the room temperature is another thing. You want to lower it as much as possible. The speed of the motor, on the other hand, is dependent or based on 2 parameters. One of them is temperature and the other is humidity, but both of them, humidity is directly related to temperature, as humidity is increased to reduce temperature, and vice versa, the temperature can be increased by decreasing the humidity. So temperature and humidity are the same factors, but the speed of fan and the room temperature itself are 2 different parameters. These are the input parameters, and the rate of flow of water is basically the output parameter. How much water do you want to flow? That is what we want to determine. So in other words, the 2 input variables are room temperature and cooler fan speed. The output variable is the flow rate of the water. And now again, like I've already done in the previous lecture, I'm going to define the fuzzy regions using fuzzy terms for input and output. For temperature, I've got 3 variables. One is temperature, one is fan speed, and one is flow rate of water. Flow rate of water is measured in milliliters per second. The fan speed is measured in rotations per minute, and temperature is measured in, let's say, in degrees Celsius. So fuzzy terms that I'm going to use for each of these 3 variables is, for temperature, I have fuzzy terms called cold, cool, moderate, warm, and hot. For fan speeds or rotations per minute, I've got slack, low, medium, brisk and fast. So I'm going to define these terminologies now. Similarly, for flow rate of water, I can have strong negative, negative, low negative, medium, low positive, positive and high positive. So these are the fuzzy terms that correspond to these three variables. Okay, so we need to profile each of these three variables and kind of connect these fuzzy terms with the variables. To connect the fuzzy terms with the variables, we need to assign them some membership functions, and these profiles have to be carefully designed after studying the nature and desired behavior of the system. The fuzzy profiles are defined for each of the three parameters by assigning membership, as I've already said. And in this case, for example, these are the three profiles. From this, it must be clear on the x-axis for the for temperature, which is on the left side. You can see that for a temperature, let's say between 1 degree to 10 degree, it's cold with some value of membership, and beyond that, it's 0 for cold. Similarly, for let's say between temperatures 7 degrees and 22 degrees, it's cool, and beyond that it's 0 for cool. Before that and beyond that, it's 0 membership for cool. Similarly, we can define it for moderate, for warm and for hot for temperature. Similarly, we need fuzzy profile for motor speed in revolutions per minute, as well as for flow rate in milliliters per second. And we can see that we have combined, or we have defined all our fuzzy terms in terms of membership functions. And these membership functions are very, very important when we want to determine this is basically the content of the knowledge base and the database, which will be used for constructing rules, as well as these will be used for determining the flow rate as well. Okay, like I said before, we need rules as well. So the fuzzy rules for fuzzy room control cooler there are going to be 8 rules. The first rule simply says that if temperature is hot and fan motor speed is slack, then the flow rate is high positive. Notice that each of these rule only specifies the terms, the input factors as an if-else statement. Number 1. Number 2, all of these are just connecting the inputs to outputs. So and the inputs and outputs are all expressed in fuzzy terms only. There's no exact values that you are seeing here. There's no crisp value that you are seeing here. So if for example, if the temperature is hot and the fan motor speed is slack, then the flow rate is high positive. Similarly, if the temperature is hot and fan motor speed is low, then the flow rate is high positive, and so on. So if temperature is hot and fan motor speed is medium, then the flow rate is positive. If temperature is hot and fan motor speed is brisk, then the flow rate is high positive. If temperature is warm and fan motor speed is medium, then the flow rate is low positive. If temperature is warm and fan motor speed is brisk, then the flow rate is positive. If temperature is cool and fan motor speed is low, then the flow rate is negative. If temperature is moderate and fan motor speed is low, then the flow rate is medium. So these 8 rules connect the fuzzy input terms into fuzzy output terms. And these are the fuzzy rules for the fuzzy room cooler. Notice that if the situation occurs such that you cannot find the corresponding rule, then the system is going to fail clearly. Then the machine will not work, and hence one of the assumptions that we have used in using the fuzzy logic control design, the assumption was that the solution must exist. In that case, since there is no rule for it, so that means that no solution exists for it, and hence our assumption is violated, and hence a fuzzy logic control system cannot be designed for it. For example, let's say that if the temperature is warm and fan motor speed is brisk, right? Okay, you do have one case for that. Let's say the temperature is hot and is warm. Yeah, or let's say if the temperature is cold and the fan motor speed is brisk, then what should we do? Well, in that case, because since there is no rule and we won't be able to define it, the system cannot work. Or that is one way by which we can look into it. Or the other way would be that we will neglect this rule. We'll assume that, if such a situation occurs, we don't have any output, we don't get anything from this. But if some other rule is being satisfied, we'll use that rule only. And hence this rule is going to be, since it does not exist, so we'll just skip it. So that's the other way. Both ways are fine. Either you say that the system is completely failed because so and so rule is not applied, or the other way would be that you just say that, because we cannot find a rule for this particular situation, we are going to neglect this situation. What I am going to recommend is that if such a case occurs, we just write we neglect this rule, and if there is no rule that satisfies the conditions, then we simply say that the system has failed. Otherwise, if there is even one condition which is satisfied, then we'll use that condition, get the output, get the values, and display it out. So in that case, we should not be worried about failure of the systems. And hence, if an exam, if a question comes like this, I will expect that you'll write that for this rule there is no there's no rule that defines this particular situation. Hence, we will not consider this situation at all. And if, for example, you have got 4 different situations, as you might see in the next slides, and out of them 2, let's say, have no output, while 2 do have an output, you will use the remaining 2 and compile your output. Let's go on and let's see what needs to be done in the next slides. Okay, so here's a small example. The fuzzifier that performs the mapping of the membership values of the input parameters, that is temperature and fan speed, to the respective fuzzy regions is known as fuzzification. That's the first step. It basically uses the input parameters and gets a crisp value from them and converts them into their fuzzy values by mapping the membership values of the input parameters. And this is the most important step, of course, in fuzzy systems, followed by the defuzzification that's done at the end and the decision making in the center. So here is the problem that you need to clearly identify. I'm going to take a particular situation. Suppose that the situation is such that at a particular time t, the temperature is 42 degrees and the fan speed is 31 revolutions per minute. So here is the 2 input crisp values. The crisp values for temperature is 42 degrees and the fan speed is 31 revolution per minute. Both my parameters now have a crisp value given to us. So now what I need to do is I now need to use a fuzzification unit or fuzzifier that is going to convert these crisp values into their corresponding fuzzy terms. So here is it. From the first figure, where we are trying to see the crisp values convert to fuzzy values, fuzzy set values using the temperature. The temperature of 42 degrees corresponds to 2 membership values, 0.142 and 0.2 for warm and hot fuzzy regions respectively. So let's go back and let's see the first figure. And in the first figure here, we can see that for a temperature of 42 degrees on this graph, it corresponds to some value on the x-axis for hot and some value for the x-axis on warm. And from this, by basically taking a cross on this, by kind of like, for example, let's say 42 degree cuts at this point, which is 0.2 or 0.143, whatever, and then it's at a much higher value for hot, which is around 0.4. Let's say this is the membership values for the temperature of 42 degrees. But kindly note one more thing. 42 degrees means that for temperature it has some values for hot and warm and 0 for all the other 3 parameters. That's the first step. Okay. Then similarly we can see that the fan speed of 31 revolutions per minute corresponds to again to membership values of 0.25 and 0.286 to medium and brisk. Let's go back and see figure 2 and see where 31 revolutions per minute is cutting the membership function. So in this case what we see is at 31 degrees on the input value over here, it's going to cut at somewhere on brisk and somewhere on medium. So it basically cuts both of these. You just need to find the intercept. For medium it is close to, let's say, close to 0.4, and for brisk it's close to 0.6 or something. Let's see what the values are for both of these. So it's 0.25 and 0.286 for medium and brisk. Okay, that's the values that it has found for cutoff. Let's suppose that that's a cutoff. You just need to take a ruler and find where the cutoff is. And that means for fuzzy regions, what we get is for the parameter of temperature, we have got warm and hot with membership values of 0.142 and 0.2. For fan speed, we have got medium and brisk with the membership values 0.25 and 0.286. That is given. Alright, that means that now if we find combinations of this, we have got 2 parameters with 2 combinations each. So in total, you have got 4 different combinations. You can either be warm and medium, warm and brisk. Similarly, hot and medium and hot and brisk with certain parameter values or membership functions that we all have already identified. So now we have got if temperature is warm and fan speed is medium, that is one combination. If temperature is warm and fan speed is brisk, if temperature is hot and fan speed is medium, if temperature is hot and fan speed is brisk. So if we compare the above combinations with the left side of fuzzy rules, which are these 8 rules that we have to identify, what you get is if temperature is warm and fan speed is medium. That's the first thing. Okay, temperature is warm and fan speed is medium. Let's go back to the rules and see where it is. Temperature is warm and fan motor speed is medium. That is going to be rule number 5. That means the flow rate should be low positive. Okay, is warm and fan speed is medium. That means you're going to go for low positive by rule 5. Then you have got warm and fan speed brisk. Okay, let's look back at the rules. Warm and brisk. That is rule 6. If temperature is warm and fan motor speed is brisk, then the flow rate is positive. Okay, so the answer to that is positive, as you can see here. Similarly, for third combination, hot and fan speed medium, we can see that it's again positive. If it's hot and fan speed is brisk, then it's high positive. Remember, if a combination does not exist, what we simply need to do is we need to neglect it. We don't need to worry about it. There does not exist a solution for it. So we simply do not count that in our possible results. Anyway, other than that, of course, we'll always count in. And if such a situation occurs that there is no rule that can be used, that means that we can then, in that case, we say that no solution exists and we'll stop at this point. Otherwise, even if one solution exists, we'll work on it. Okay, so now what we get is we get low positive, positive, positive and high positive. We get 4 values, and there is some kind of conflict here, and the fuzzy region that is to be given as a value for a parameter water flow rate needs to be resolved. How do you resolve it? Okay, the fuzzy outputs are basically low positive, positive and high positive. They are to be converted to a single crisp value that is provided to the fuzzy cooler system. And of course, this process is called defuzzification. There are several methods that exist for defuzzification. Of course, there are 2 methods that are really common. The one is the center of gravity method, and the other is the composite maxima method. The centroid of a 2-dimensional shape X is the intersection of all straight lines that divide X into 2 parts of equal moment about the line, or the average of all points of X. So that's the first solution. In both these methods, the composite region formed by the portions A, B, C and D corresponding to rules R3, R4, R5 and R6 respectively on the output profile are to be computed. And I'm going to show you the regions here. The regions here are, you have to identify here, for a temperature 42 degrees centigrade given here and motor speed of 31, you've got the first case, which is hot and medium. In case of hot and medium, what you get is at 31 degree it cuts at around 0.25. In case of hot, it cuts at around 0.2. And if we take it to the value of 0.2 on the according to rule R3, if we take it to the value of 0.2 and basically we cut the positive region on this, we see that the water flow is coming out to be this region, this whole region, which is C region. As you can see here, this is the region that gets cut out. We need to find the center point of this, which is close to this point, which is 1.1, let's say. So the flow rate of this is going to be 1.1. Okay, notice one thing. The degree of membership for hot is 0.2 and the degree of membership for medium is 0.25. We need to find the minimum of these according to the to our first method of inference. After finding 0.2 and 0.25, which are the membership values, you need to get the minimum of them, which is 0.2, and then from this 0.2 you need to basically mark a line on the output figure for the flow rate, and in that, of course, the region that we interested, since from the rules we know that it's positive, we are just going to take positive. For hot and medium it was positive, as you can see here, and yes, for hot and medium it was positive. So all we did was on positive, because this was 0.2 was the value, so 0.2 on positive, we consider that on 0.2 on positive on this region, and it basically cuts it on this point, and we need to find the centroid of this whole point. The centroid will depict us the speed. The centroid comes out somewhere close to this, which is 1.1, and that is going to be your motor speed according to the first rule, R3. Okay, so from this the answer that we're getting is 1.1. okay, then let's move on and let's see what the answer what is the answer that we get for this. For temperature of 42 degrees and motor speed of 31, the other thing that we identified is that the weather can be hot, the temperature can be hot, and basically the fan speed can be brisk. And then if we compute the membership functions on 41 degrees, for 42 degrees and on 31 fan speed, it comes out to be, the membership value again comes out to be 0.2, since 0.2 is the lowest value between 0.2 and 0.286, which is this value. So from brisk we are getting 0.286, from this the membership value we are getting is 0.2, the minimum of them is 0.2. Again checking 0.2, but this time with high positive, since the rules basically suggest, rule R4 suggests that with hot and brisk it is going to be high positive. We get this region, again we compute the centroid of this region, and the centroid is corresponding to, let's say, 1.25 revolutions or milliliters per second for the flow, and the answer for this case is 1.25. So now we have got two different values. Okay, similarly we can compute it for the third value, and for the third value again this is going to be the minimum of 0.2 and 0.142, and this corresponds to a value of let's say for the low positive, using rule 5 we are going to be close to 0.95 or something milliliters per second for the flow rate. So this is for the third one. Similarly for the fourth one, again it's going to be 0.142 is the minimum value, and 0.142, if you combine that, if you use that to for this particular function, you're going to get to close to again 1.1. okay, so now you've got four different output values, and what we need to do is, we need, for all of these different values, we need to find the centroid. Okay, so we have got four different regions now, like I said, A, B, C, D, and all of these regions are corresponding, are colored here, as you can see, they're crossed, they're crossed here, and now we need to find centroid of all these regions. The centroid of all these colored regions comes out to be this particular point, and if you look at it, this is close to 1.1 milliliters per second. So you need to take all the regions A, B, C and D into account on the same figure, and after taking them on the same figure, you need to find the centroid value of it. Of course, for us the y-axis in this particular output does not really matter, because for centroid the x value is the most x-axis value is the most important, and in this case the x-axis value represents the crisp output that we are going to give out, and you can clearly see here that the crisp output here is close to 1.1, and that's the crisp value that you're going to give as output. So with that, this is the exact example. I can possibly give you any two parameter values, and you need to be good enough to look at rules yourself. You need to identify the regions using those rules. You need to identify the membership function values. You need to find the minimum of those membership function values, and using the minimum function values, you should be able to find the interesting regions for your analysis. And of course, after finding the point of interest, then what we need to do is we need to find the centroid. And then the first method and the second method, it's kind of similar as well. If you find the centroid, the x-axis value of this particular region is going to be the crisp value that you're going to output for your for your solution. So in this case, for example, the crisp value that I got for a temperature of 41 degrees 42 degrees and fan speed of 31 revolutions per minute was 1.1 milliliter per second as the flow rate. You should be able to find it on your own given any parameter values and given any other problem as well. I'll give you the rules probably, I'll give you the membership functions, and then I'll ask you for a given input parameter values of variable values. You should be able to determine this crisp value on your own. Okay, so if the example is clear, I need to wrap up this whole lecture, this whole section, and for that I'll basically tell you that what are the key application areas of fuzzy logic where fuzzy logic has been applied in a lot more detail. The first one is of course the aerospace industry, where the altitude control of spacecraft is usually done for autopilot systems. The satellites are basically the altitude for satellites is also controlled using the same system, and similarly the flow and mixture regulation in aircraft de-icing vehicles is also done using fuzzy logic in the aerospace industry. Then from aerospace industry, if we come to automotive industry, which is the cousins of the aerospace, again in automotive industry, fuzzy logic has been applied in a lot of different areas, sub areas or subfields. The trainable fuzzy systems are used for idle speed control in a lot of cars. We can shift scheduling methods for automatic transmission. For example, going from first gear to second gear or something, so gear transmission is kind of controlled using fuzzy logic, as those who drive cars and automatic cars can kind of identify. Then there are intelligent highway systems that can be used for that are being designed by fuzzy logic. For example, that detect how many cars are coming and which light should be opened, which light gets the priority. Similarly, it could be used for traffic control on a given day or on any day at a given place. They are highly useful for that purpose as well, and highly applicable and suitable. They can use to improve the efficiency of automatic transmission as well, as has already been mentioned earlier. Similarly, they've been used in business for decision-making support systems and for personal evaluation in a very large company as well. By just seeing what kind of work has been done by a person, they can be used for personal evaluation. Then they have been used a lot of times in defense systems, especially in underwater target recognition, for automatic target recognition of thermal infrared images, for naval decision support aids, for control of hypervelocity interceptor, for fuzzy set modeling of NATO decision making as well. They have been used in a lot of defense related industry and defense related decisions. We saw an example of how they have been used in electronics in a room cooler, for example, in this lecture. But there are many other important usages of these as well. For example, in electronics directly. For example, control of automatic exposure in video cameras, humidity in a clean room, air conditioning systems, washing machine timing, microwave ovens, vacuum cleaners, and so on. So they have been used in a lot of different electronic equipments that are specially available to us as consumers. So that is where they are directly being utilized, or where we can directly view them at work. Then they are used in the industrial sector, where cement kiln controls, heat exchange controls, activated sludge wastewater treatment process control, water purification plant control, quantitative pattern analysis for industrial quality assurance, control of constraint satisfaction problems in structural design, as well as for control of water purification plants. So this is one region where if someone among you wants to work with, let's say, someone from the civil engineering department or from the chemical or materials department, I think this is one place, one area which you can clearly apply on their problems. So maybe for your FYPs, if someone of you is intending to work with the batchmate from other faculties, this is exactly the place. This fuzzy logic is exactly the key application that you can offer to them. The fuzzy logic has been applied to manufacturing industry as well, for example, for optimization of cheese production, for optimization of milk production, etc. It has been used in psychology, and fuzzy logic based analysis of human behavior has been done. Criminal investigation and prevention based on fuzzy logic reasoning has also been applied in psychology. Other than that, it has been used in marine studies. For example, autopilot for ships. It's the same way as it's done for speed control on cruise mode. That's what we call it. On roads for automobiles, and for altitude control on aerospace and satellites. It's the same thing for ships. We can use fuzzy logic for optimal route selection as well, for control of autonomous underwater vehicles as well, for ship steering. So these are some of the usages of fuzzy logic in marine. Similarly, they have been used in medical sciences as well, for medical diagnostic support systems, for control of arterial pressure during anesthesia, for multivariables control of anesthesia, for modeling of neuropathological findings in Alzheimer's patients. Maybe in this case, Dr. Shahab Ansari can give you more information of how it's used in Alzheimer's patients. It's used for radiology diagnosis. It's used for fuzzy inference diagnosis of diabetes and prostate cancer as well. So here you can see that how fuzzy logic has been used in various diseases, as well as for controlling the amount of medication that one gets in a particular disease or in particular situations. It has been used in the security department as well. So it's used for decision systems for securities trading. It is used for various security appliances as well. And we might ask GIK to use it for controlling or managing the security of the department as well. It's actively used in transportation, where it's automatic underground train operation, for example. It is used for train schedule control. It is used for railway acceleration. It is used for braking and stopping of trains and other transportation as well. So the take home message is that there are a variety of fields in which the fuzzy logic has been applied, and what we get is, apart from all these fields, you can see, for example, pattern recognition classification. It is used to identify or recognize the speech. It is used on speech recognition. It is used for handwriting recognition. It is used for facial characteristics analysis. It is used for command analysis. It is used for fuzzy image search. It is used in finance for banknote transfer control. It is used for fund management. It is used for stock market predictions. So there are endless applications of fuzzy logic, and I think I chose to teach fuzzy logic in this course because, one, it was a very important topic. The other, it has a lot of application and it's a very interesting topic. So if you go away from after this course, I think you'll be able to identify, or you'll be able to tell about a lot of different techniques of soft computing that are very useful and that can be used for your analysis. For fuzzy logic, you need to have a different way of thinking altogether, and that way of thinking is really the most interesting take home message from this lecture, at least, and section 9, all the section 9 from 9.1 to 9.4. Okay, so this kind of brings us to the end of our lecture. Now we're going to summarize the key points. First of all, fuzzy logic has several key applications in control systems, and we have seen the different areas where they've been applied in one way or another, and you can kind of think on your own. That would be the challenge for you guys to do, that think of your own, that how it can be applied to a defense system, for example, or to a particular application, to finance, for example, to trading, for example, to something like that. How can a fuzzy control system be applied to that? So you need to think of it. And maybe design a system. I can give you the question to design a system on your own in a particular application, and that would be really interesting for me to see how you design it and what you come out with. So as an example, we have seen in this particular lecture, we have seen that how fuzzy logic can be used in a room cooler to control temperature, and you can basically use different configurations of the temperature and fan speed to see how much water would be flown through. We have also seen various key applications areas of fuzzy logic, ranging from electronics to industrial sector as well as in medical and security and finance and so on. So this is kind of a very motivating field, a field which has got a lot of applications. Maybe you can select your FYP in using fuzzy logic with any of your other colleagues from other departments even, and this is something that they are regularly using. So this is really interesting and really important as well. And I'm just going to give you a small bit of anecdote here as well. So when we went to for BS in AI program and we presented the curriculum of this BS in AI program, a question that we had from a head of department of another department, from chemical and materials engineering department, we had this request that you have designed this whole curriculum for AI, but I don't see a single course on fuzzy logic. And that was kind of a bit embarrassing for us as well. Not really embarrassing, because for fuzzy logic, as you have seen here, is just a topic which can be, of course you need to have domain knowledge for this, and you need to have a complete expertise and control on the system to basically be able to work with it. But this is just a topic that if you have the other pretext ready and done, if you have the domain knowledge, all you need to do is maybe have just like, let's say 2 or 3 weeks lectures on this fuzzy logic in total, and you don't really need a whole course. So, but it was so important that they thought that it must have its own whole course, although for us guys it's just a small thing to do. It's just a bit of mathematics involved, membership functions, fuzzy set and fuzzy mathematics, fuzzy logic principles that are needed, and that's it. So you've seen that we have done this in kind of 2 weeks lectures, 2 weeks worth of lectures, and this was really a very interesting topic, and hence I've been I had kept it in this course, and I tried to be as much descriptive with an example, with a case study, although you don't have any other case study for any other topic, but this one was very interesting, and so I went on with a case study for this. So with that, I'd like to end this lecture. In the next lecture, I'll just go through the contents again and kind of talk about what we have done in each lecture. So that would be a kind of overall course review, if you want to call it. The fuzzy logic part has ended now. We are done with the fuzzy logic. We have seen practical example. We have seen the mathematics that is underlying this. We have seen how a system is designed and the key assumptions. So you can verify that all the key assumptions here are met completely. And like I've said, if a solution does not exist, then the key assumption of having a solution will be violated. Other than that, I wish you all the best, and I hope that you were able to learn something from me in this particular lecture and in this particular lecture series. Thank you so much. So this is a list of additional reading that you might want to do. They're also given as link in the video. Thanks for listening. Hope you learned.